Okay, gonna stay in the middle here. Hi everybody, Kia ora. My name is Michael Schröder. I'm a PhD student at TU Wien in Vienna, Austria. My PhD advisor is Jürgen Zito. I realize I maybe should put my slide. I want to tell you about grammar inference for ad hoc parsers today. So this is an ad hoc parser. So this is a simple Python expression. Could just as well be expression in any language, may even be a valid JavaScript expression. But let's say it's a Python expression. All it does is it takes some string s here, which is supposed to be a string of a list of comma-separated numbers, and it turns it into a list of integers using these standard functions like split and map and Python int constructor. Now we call such an expression an ad hoc parser because, well, first of all, it's clearly a parser, right? It turns a string into some kind of structure type. But it is completely ad hoc. It uses these common operations, but it doesn't use any formal parsing techniques. It doesn't use any parser frameworks like parser combinators. And the underlying grammar that it is parsing remains entirely implicit. It is parsing something, it is imposing a structure on the string, or it is assuming some kind of structure, but we're not explicit about what that is. So here is the grammar for this parser, with a textual form and an equivalent visual form. And this grammar is a complete but finite description of all the possible values that this string s can have without the program going wrong. So in this case, actually, if you put any string in this variable s that is not generated by this grammar, then the program will actually crash. And I think there's an analogy here with types, right? A parser without an explicit grammar is kind of like a function without an explicit type signature, right? It might still work fine, but you will only know if you actually run the program, if you actually parse the string. Whereas if you knew the type or if you knew the grammar, you could reason about the program or the parser beforehand. Now, obviously, for such a simple expression, nobody will actually sit down and write this grammar. Even though this is quite a complex grammar for such a simple expression, you wouldn't actually stop and think about it. Now, I mean, with types, you also always sit down and write a type annotation for every single sub-expression because we have type inference. Like even in an untyped language like Python, we can very easily infer that this string s here, that this variable s here is a string just based on the operations that act upon it, just from the surrounding context. Now, what if we could also infer the grammar of this string based on the surrounding context, right? What if we could infer not just that this variable s is a string, but that it is a particular string that is described by this grammar? So if we could do that, then it would open a whole range of new possibilities. Like, we could show this grammar to the user, provide a kind of interactive documentation. And since it's a grammar, we can already generate some, example inputs of things that can be in this string or that are not going to be in this string, right? We couldn't go much further than this. You can imagine some kind of bot in your CI pipeline that tells you on each commit, hey, this commit actually changed the input grammar for your function and introduce a semantic change. Is that really what you wanted to do? And there's many more applications, and I don't have the time to talk about all of them. I gave a talk at ICSI on the new ideas track earlier this year, where I could go into more detail about some of these. So if you're interested, you can look that up. And one thing I want to point out maybe is grammar-based fuzzing, because that's a thing that's kind of a lot of people are doing nowadays. Where if you can statically infer the input grammars of a function, you can then use those grammars for fuzzing, which allows you to penetrate deeply into program states, because it bypasses all these initial like ad hoc parsers that kind of validate your inputs, right? Because even though the input is syntactically correct, it might trigger some other weird thing in your program. So we have all these cool things we want to do, right? So our goal in order to do it is automatic grammar inference. But how do we get there? How do we get from some piece of ad hoc parser source code to some grammar specified in this kind of high-level way? So since we are PL researchers, obviously the answer is we invent a new programming language and we give it a cute name, hence Panini, which it's actually more of an intermediate representation because it's not meant to be written by hand. It's meant to be auto-generated. Panini is really just a very, very simple lambda calculus in a normal form. And the only thing that's special about it really is that it has a refinement type system in the style of liquid types, which is what liquid Haskell uses. You might have heard that. And the other thing is that, so if you look at this Panini program, this is an actual Panini program. You can put it exactly like this in our prototype system. You can see here we have this kind of parser, this kind of lambda function here, which is the equivalent to the Python source code here. And up top here we have these kind of type signatures for all the functions that occur in here. and we only have these types of images. We don't have any definitions for these, right? Which also means we cannot actually run a Panini program, but that's okay. It's only meant for type inference. So we have these string functions here just as axioms, basically, and we have our parser translated into this Panini thing. And then the idea is we want to infer the most precise refinement type for our input string. And that hopefully tells us something more than it's just a string, right? It hopefully tells us, gives us more constraints. Now, before I continue, just a really brief 3-slide crash course in refinement type, so everybody knows what we're talking about. So a refinement type is really just a regular type with some refinement. So we can say we have some base type like int here, and then we can say, well, we're only interested in integers that are greater or equal than 0. So that basically specifies the natural numbers. And this refinement, you can choose any kind of decidable logic that is interesting for your domain that you want to refine. Like usually something like quantifier-free linear arithmetic with uninterpretable functions, something you can send off to an SAT solver to kind of worry about. I guess you could choose an undecidable logic too, but I don't know how you do that. Then you also have dependent function types. So output types can refer to input types, which allows you to specify something like a string length function, where you get a string as an input, and the output is some integer that is defined to be exactly the length of the string. This mathematical length function here is on the level of the refinement type that allows you to then associate those variables. And so when you type check a refinement type system, or when you infer the type for a term, you don't just get a type, you also get a verification condition, which is some kind of usually universally quantified constraint that arises out of the interplay of your types. And you need to set that off to an SAT solver like set3. That needs to determine that this is valid, and then your types check out. If the SAT solver says it's not valid, then you have some kind of type error in your program, right? Okay, so if we now use refinement inference on our Panini program and try to infer refinement types, we end up with this. We get this weird little kappa variable as a refinement, and then we have this verification template, which kind of arises from this process. And these kappa variables, they represent unknown refinements. So our refinement inference cannot really tell you what's in there, and you have to solve this somehow with some other means. And so refinement systems like Liquid Haskell, they use sophisticated algorithms like the fusion algorithm to very efficiently but also precisely solve these constraints. So for most programs, we can precisely solve these kappa variables and know exactly what is the most precise constraint that we can put in there, and in an efficient way. Unfortunately, the existing approaches struggle exactly with those constraints over input strings, which I call grammar variables. It's just that they can't really do that. So we have to find a way to kind of figure out what goes in there. This is really what we want to know, right? This is the refinement of the string. But fortunately, the refinement inference already gives us a lot of information. So it gives us this verification template, and basically we need to make this valid, right? How do we make this valid? Well, we have to find something that goes into kappa 0 here to make this application valid. And so the idea is we base this solution on this what I call the grammar consequent here. It's not a good name, I think, but I haven't come up with anything better yet. So because basically, if you put this into the antecedent of this application, obviously the thing implies itself, right? We cannot take this as the solution because it has universal quantification. It has maybe some integer stuff in there. It's also very huge and unwieldy, and just basically is equivalent to our program, so that doesn't gain us any information. It's not really helpful. So we want to minimize this somehow, right? And so this is exactly the same grammar consequence, just presented in kind of a tree form because it's easier to visualize what's happening. And what we're doing to minimize it is we're rewriting this tree from the bottom up, and we apply certain rewrite rules and Boolean equivalences. We eliminate quantifiers by resolving equations, and in the background we use precise abstract value representations to deal with this stuff. So like lattice operations, lattice algebra, and so on. So I'm not going to go through every single step now because it will take too long. I gave a talk at the type-driven development workshop earlier this year where I go through every single step. So if you're interested, you can look that up. But just to give you an idea of kind of the flavor of what's happening here. So we basically kind of, on the one hand, we look for certain patterns in there, which we can just, simplify using Boolean equivalences and so on, and then kind of make this tree smaller, right? And we go then up the tree and do this. And then eventually we get to universal quantification, and we can eliminate that by then resolving the variable that is quantified in each of the branches. It allows us to eliminate some branches and to eliminate the variable in other branches. And then we just do this for the whole tree, and we kind of make it smaller and smaller. Oh yeah, and I forgot to mention, the goal here is to reach a disjunctive normal form. Why disjunctive normal form? Because that very neatly kind of maps onto the way we usually think of as grammars with like alternate production rules. It's kind of like a natural way to think of this. And so we just continue on and on and on and simplify this, and you can see it always gets smaller and smaller until finally, at some point, we reach a minimal string predicate. And then we can take this, we can put it back into our verification template, send this verification condition off to an STT solver, which hopefully tells us, yes, this is valid. Or it might tell us it's not valid, either because we made some mistake in the simplification, or we may have uncovered a new type error in our program now that we have this more precise refinement here. But what we can also do with this minimal string predicate is we can kind of view it as a grammar and then show it to the user or pass it on to some applications. So just to kind of recap here the whole thing that we're doing. So we start off with some ad hoc parser source code. We transform this into our intermediate representation Panini. We infer some string constraints from that, and then we use this grammar solving stuff to minimize those constraints and turn it into a grammar. So this part here, we've implemented this. This works fine. This part here, the grammar solving part, we have a prototype implementation that can solve exactly what I've shown you before on the slide. We can put it in the system and automatically solves it, and similar programs. But we are currently still working on like formalizing this step and also finding out what really are the limits of this. I mean, a lot of this is dependent in the background on kind of the abstract domains that we're using to internally represent these values and the strings and so on to solve these. Like, obviously, for the integers in our program, we can choose different domains like, polyhedra or whatever. Right now, the prototype just uses integer ranges, and that seems to be enough for the simple programs we're looking at. But obviously, if you want to look at more complex parsing programs, then we would need more complex ways to represent this stuff and to resolve it and work with it. And the same, of course, with our string domains. So this is still ongoing work here. Now, obviously, this whole front part here, so we know how to turn imperative source code into like these a normal form lambda functions, but it's not entirely trivial, because of course you're never gonna have some kind of just one line of a little bit of code that is just an ad hoc parser. You're gonna have a whole program, and you need to find those parts that are actually just the ones we're interested in. So we need to do some program slicing, which is far from trivial, And also, we need to really know how to translate the original string operations into Panini. Like we need those axioms, we need those string specifications. Somebody has to actually sit down and write those and make sure that they match the semantics of what's actually happening in, Python version 3.0 or whatever, right? So there is some effort involved here to do that. But we're tackling that. That's what we're gonna do next. So the whole thing, of course, we want to have an actual working system. So there's a lot of engineering involved here to make this work really end to end. So one thing, for example, I haven't mentioned at all is provenance, right? We want to be able to kind of trace back grammar productions that we can infer all the way back to the source code, because that allows us to debug things, that allows us to give kind of traceability to the end user program, right? But doing this kind of preserving the provenance of these things through all the transformation steps is like not trivial. I mean, that is some engineering effort. So eventually, I also want to build some of these applications as prototypes that I've shown you earlier, just also to demonstrate the effectiveness of the system. And we also want to, of course, evaluate it. We want to evaluate against a corpus of ad hoc parser samples that come from the real world, also against other approaches to mine input grammars. So right now, we have a study ongoing to mine these ad hoc parsers. So if any of you ever come across in your work some piece of code that does a little ad hoc parsing, even if it's very trivial, please send it to me, because I like to see real world examples of these things. Even if you think it's trivial, that's actually also very interesting. Eventually, once the whole system works, we want to do a mining study of inferred grammars. Let the thing loose on all of GitHub or whatever, and see what are the grammars that are actually in programs. We see, and then compare these. Like, oh, people are trying to parse email addresses and in these different ways. So we have these grammars with these slight subtleties and differences. And also, to kind of show you the kind of scope of this whole thing, this is somewhat orthogonal, but we also are currently prepping a user study on grammar comprehension. So one of the use cases I showed you was we just show the programmer the grammar, and that helps them maybe understand the program. But does it actually help them understand the program? I mean, my hypothesis that it does, even if a programmer can't necessarily write the grammar. I think seeing it still will help you debug a program, but we're trying to find that out. I think I'm right on time. So yeah, that was a little bit of overview of my work, and I'm ready to take questions. Thank you. Yeah, sure.
Sorry, I was late, so I apologize if you already answered this. Sure. But you mentioned that you needed to extract the specifications of those string functions.
Yes.
Yeah, is there a way to automate that?
I mean, we were thinking about this. I mean, right now we're just writing them down by hand, right? But yes, it would be nice to automate it, or at least be able to automatically check. But it's difficult. For example, if you think of like hyphen, you have those in the documentation somewhere. I mean, you could look at the source code, obviously, but then that's a whole other can of worms. It's like to extract the switch bit there. I mean, you need to. The easiest way is to look at the easiest ways to get some students to look at the code, at the documentation, and then write the axioms down, and then somebody else check it that this is true. I mean, unfortunately, that is kind of the manual part you do, but you only need to do it once, for every programming language you use. Oh, sure, yeah, and then you can test it in various ways to make sure that these axioms are correct. But yeah, I mean, it's not insignificant effort, but I think it's like manageable. Sure.
I'm interested in the user study of grammar comprehension.
Yes.
Because I'm interested in user studies of programming. Yeah. By that you mean grammars presented how?
Well, yeah. So the idea is you give them a piece of source code and a grammar in either like this form, like in either of these forms I showed you earlier. Like you can set them visually, like a railroad diagram kind of thing, or in these like production rules, like EBNF style kind of grammars. Like these kind of very classic, like context-free grammars, basically. Or like in the style of like this kind of how you represent a concept.
But do you mean generally those notations, or do you mean the kind of ad hoc parsers like you were talking about that we actually see in programs?
Yeah, we will give them a piece of code that has an ad hoc parser as a piece of code, and we also give them the grammar. And we have like a control trial. Some of them don't get the grammar, some of them have the grammar, and then need to answer questions about the program or debug the program. And we want to find out if having the grammar, if that helps you reason about what are actually the inputs of the program, because it's just a different view of your program. It's kind of this spec in a way, right?
Okay, well, so a related question that I was wondering about several points in your example. What about regular expressions?
Oh, sure. So regular expressions, I mean, they are one of the few examples of kind of a widespread success of people actually writing grammars by themselves. But there are some studies. Actually, it's people get them wrong all the time. They don't know what they mean. There were some studies that don't have to cite it here, but they get them wrong all the time. And also, there's a big problem of every programming language has their own proprietary different version of regular expressions, and they're just slightly different. And once they get big enough, this makes a difference. And then people think they do one thing, but they're actually not doing it. And so even if you have a regular expression in your program, if you can extract another type of style of grammar representation, that is also helpful, because it gives you again another view of this. But usually, so what we see is that these kind of ad hoc parsers, they sometimes include regular expressions, like small regular expressions, but then also often if you like, say you have a piece of string you want to split on commas, you often just call the split function, and then you get something out of it, and then maybe the start part, you have a little regular expression, but you kind of usually mix and match these things together. And the kind of combination of all of this is really, I think, the interesting part. And then kind of a bigger grammar. Yeah, sure.
It's just a comment, but I have seen work on grammar inference for programs that output in strings in the context of checking validity of dynamically generated HTML. How do you compare? I mean, I think your technology can apply to that setting.
Yeah, it's similar, but it's slightly different. So in the field of like string constraint solving, there was a lot of focus and a lot of works on yeah, I'm trying to find out what are the types of strings and programs output, also to prevent stuff like SQL injections and so on. With like, because a lot of websites, you just concatenate together different strings and splice in like variables and so on. And that is similar work. So our view is kind of from the opposite, because we want to know what are the possible things that can go into the program, whereas this is what goes out of. And they are very related. We can use similar techniques, but in the end, it's kind of different, because often they want to ask specific questions of, can this string be represented in this? Or like these string constraint solving is usually you have some kind of question you wanna answer, right? Is this satisfiable? Are these constraints, if you put them together, can this be produced? Can the program reach this state? Whereas we want to know what are all the possible strings that you can put in without without the program going wrong, which is a bit, I don't want to say it's more difficult, but it's different. But yes, they are related.
Yeah, I wonder if the core part can be shared.
Maybe. I mean, the thing is, so I'm really focusing on these kind of input strings, and I want to like exploit everything I can in order to be able to do that, which also means that maybe the other direction is not so easy then, because, but yeah, I don't know. Yeah, sure.
What are the properties of your grammar solving? Is it sound? Is it complete?
Well, the short answer is I don't know. The long answer is I don't know yet. So I'm working on it.
I like all your answers. Okay, good. Another question, a bit of a follow-up on Robert's, but you're doing a user study, interested in doing a user study on grammar comprehension, or already doing it. That's cool. But what does comprehension really mean? Right? And is that what I really care about?
Yeah.
Maybe I wonder, is it worth doing a user study that ties to the claims for what this is useful for, which I think was mostly not about comprehension.
Yeah,
more about
that's true.
I want to edit my code, or I want to find bugs in my code. Or,
I mean, the thing is also, it's just, I mean, maybe it's like an additional explanation. So we planned to do this user study a while ago, but for various reasons it's got delayed, and so, but we still want to do it, but it's now like kind of the thing. But I still think it's very interesting. And we would define comprehension more in a way of like, can the programmer answer questions about their code, understanding it, like what are the possible inputs? Can you generate inputs for a code that would pass in order to produce failures? Or there is an error in this code, can you locate it? Right?
Okay, so you actually are thinking more of those.
Yes, more along those lines. Yeah.
It's always, I mean, this is the key when you're evaluating things, right? Are you actually asking the right question? Or are you gathering the data that's closest to the claims that you want to make in your big picture, not just in this small statement, right?
Yeah. And again, I might link back to the cognitive dimensions model of Green et al. We have a number of ways of cutting it, of partitioning these kind of activities that you want to do. But it sounds like you're really on the right track there. I think that's really interesting, because this has been lurking in all kinds of programming language related things for half a century. Frankly.
Yeah, strings are everywhere. It's like inescapable. I think, yeah.
Thank you for the great work. This is not the first time I have listened to your talk. That said, one thing that you mentioned is that you have to do a little bit of manual work to extract the string grammar for these particular functions.
Mm-hmm.
I wonder, these string functions, their grammars are not likely to be extracted.
Yeah.
So I wonder if the black box grammar mining that we currently have can be applied, so that you can tie it both together and then you can avoid this manual extractions.
Maybe, I mean, and also the kind of hope is that, maybe it's enough to specify a few primitive functions and the rest we can kind of come together. I think that the difficulty is always like, there's a real danger lurking here if those specifications are not quite right, that you're getting a completely wrong picture, because like in Python version whatever, the I don't know, split function is defined in a very particular way with some quirk in there, and you need to capture that exactly, right? And the danger is, of course, if you don't do that, then everything falls apart, because everything you're kind of deriving from this then isn't correct for this version of Python anymore.
It depends on what you want to do with it, whether you want to be sound or complete.
Yeah. No, I mean, if you want to generate grammars for fuzzing, obviously it's maybe not so important to be exactly like, complete or sound or whatever. It's fine if you get there somewhere. But yeah, as soon as you want to make some guarantees of, hey, this is exactly the grammar, and there is no other string then you need to, that's fine.
The nice thing there is that you only have to do this once for every.
Exactly. I mean, so I don't feel it's like such a big problem. It's just work here. It's effort, but you need to do it only once. There was, yeah, yes,
Yeah, so it's like, a technical question. My question is that how you got the motivation to use the word Panini? Because of the breadth or the grammarian of
both.
language?
Both. It's a double pun, yes. It's both the Sanskrit grammarian and the British
The question I had, because in a couple of minutes you know. So,
yeah.
So my question was, do you have any feeling of how prevalent these ad hoc parsers are and in which kinds of applications?
Everywhere. Think of any program that takes an input from standard in. Like you're parsing the input somehow. Maybe you're using a framework to parse it, but I mean, often you don't. Anytime you manipulate strings, you're using ad hoc parsing. And often this is intermixed with, it's called shotgun parsing. This is intermixed with your business logic somehow, right? It's not neatly the beginning of the function, we parse everything, and then we continue with our cool data types. No, we're parsing a little bit here, then we see perform, we're parsing it there. So you have these little snippets of code that parse everywhere. You just need go on GitHub code search and type in, I don't know, split or whatever. And you find like it's everywhere. Like these parsers really are very widespread.
This might also be particularly interesting in things like Excel or so, where like I don't know how many people use regular expressions there. They can at all, right?
Oh, I'm sure there's some gnarly Excel spreadsheets. Yeah.
But you often have these like left and right and find all of these things because you need to parse them.
That is interesting. Yeah.
That's so tedious.
Yeah, very much.
Expressions.
But then
People do it. I think that was right.
Yeah. So I think the assumption is that when one uses ad hoc parser, usually the syntax is very simple, and that's why like it's also kind of intermixed with the business logic.
Yeah.
It's just so trivial piece of code. And well, like from my personal experience, like when I wrote my compiler, I had 3 places where I had to have a ad hoc parser, basically for parsing county files. But I just for these 3 different county files, I just share the same syntax, and I give the users a very brief, informal description or documentation in that English, saying that every single line you have an identifier. Sure. That's it, right? So, like, how do you compare this, like, just a very simple informal description versus a formal grammar? And as you said, like, people usually get regular expressions wrong.
Yeah.
Then I think it's also there's a chance that people will get formal grammars wrong.
Oh, sure.
Right?
Yeah. No, of course. I mean, there's a guarantee that you will be understand it, but this with any form of specification, at least if we have it in the form of a grammar, we can automatically do stuff. We can synthesize a different version of the program. We can check it maybe against it. And so, like, if you have the grammar, you have a specification in some kind of formal way that you can do stuff with. As far as how much can the user understand, yeah, that's wrong. But if you have a grammar, you can automatically generate test inputs, for example, and show those to the user, which are very helpful. And if you manage to really preserve the provenance, you can imagine a plugin where you hover over the grammar and it highlights the piece of code that is responsible for that production in the grammar. And then you can really try to get an understanding of how the grammar, why it is the way it is. So,
yeah, I think I had a real use case, like when these things very helpful, where like I require an identifier on every single line of the file, and there was a case that like it just didn't parse. The reason was that there's entry in white space.
yeah, white space is a very common issue that people are not considering, and that becomes obvious if you don't have the grammar, because then suddenly, oh, what's on this? Yeah, this is actually I don't want to go back all the way now, but in the beginning, this little passage from the beginning, there is some trickery with white space there and digit grouping in Python that nobody is aware of, that you can do this with like underscores between numbers, and that's a valid thing that Python accepts and so on, and it was very surprising to me when I found this out. So, yeah.
String is magic. Do we have any sort of final comments? No? Great discussion.